continue with our ideas of square roots. And now we're going to start talking about the idea with a negative under a square root, which we haven't gotten to yet. All we've done was attempt to simplify and solve equations that have real answers. But now comes the question here, how do you consider to solve this equation? Okay, and this is how we started off last time. If you remember, last time we talked about how do you solve the equation x squared equals b, or x cubed equals b. And that's what discovered, or that's what invented in a sense, our square root, our cube root, or our nth root. But now we're thinking about the following. What if we have the equation x squared equals negative 1? Well, we know that there's no number that can multiply by itself to give you a negative, because any number squared is positive. So even if you started with negative 5 squared would still be 25. Or if you started with positive 7, it's 49, and so forth and so on. But the idea is that whenever you square something, you get a positive. So how do you solve this equation? Okay? So what happened was, to solve this equation, the number I, or the constant I, was invented. Okay, that's really where it came from, to solve this equation. Now, by definition, what we're going to call I is the following. We're going to say that I squared is negative 1, okay, which is the solution to this equation. If you look back up here, okay, that's what the solution would be from that equation. I squared is negative 1. And by definition, though, we're going to say that if I squared is negative 1, then I is just the square root of negative 1. Again, take a look at this. If you square rooted this side and you square rooted this side, this is what you would end up with. Okay, and this is the key that we're going to really use a lot of. We're going to definitely use this other definition on the right over here. Okay, we're still going to use the other definition on the right. Okay, so we're going to use both of them. But it's the one on the left that's going to be more useful right away. You'll see when the one on the right will become a little bit more useful later down the road or later in this lesson. Okay? So what we're pretty much saying is the following. We're saying that if we have the square root of a negative quantity, we break it up into the square root of negative 1 and that positive quantity. So again, if this were the square root of negative 5, this would be the square root of negative 1 times the square root of positive 5. You always break it up, you take the negative 1 out pretty much. Okay? But then by definition, the square root of negative 1 here that you're seeing is what I is by definition. I is the square root of negative 1. So instead of the square root of negative 1 here, you replace it with that I as a constant. And whenever you see an answer that has an I involved in it, you know that at some point in time, a square root of a negative quantity was taken. Okay? Square root of a negative quantity was taken. Now, the many uses of this, believe it or not, there are far many more uses than you would actually think. In almost any sort of engineering degree, you're going to see imaginary numbers all over the place. In the science field, you're going to see imaginary constants. Okay? Honestly, though, outside of math and science, you're not going to see it very often. Like, you're not going to probably look at imaginary roots, say if you're going to study liberal arts, or if you're going to study, poetry or something like that. Yeah, you're not going to even see math in general, but you're specifically not going to see this. Okay, but it's extremely useful in any science technology field. You'll hear about the imaginary part of the problem having a big component or a big effect on the results. Okay, so electrical engineering, systems engineering, like I've talked about before, cruise control, that idea. Well, cruise control, the way it works is it looks at the feedback. Okay, and it determines, am I going, say I want to go 75. If I'm going 74, well, that means that they're going to automatically, the cruise control in the car will automatically accelerate the car a little bit to get up to 75. The minute you're going too fast, say you're going downhill now, and your car starts coasting down to like 78 or 79 miles an hour, well, then it's going to apply a brake automatically. And the feedback mechanism that it uses are actually imaginary and real roots and poles, they're called. And based on those values and those quantities, it knows whether to speed up or slow down. Okay? So it's a very good application of it, but you don't see that happening because the car's computer system is what does it. But this is what's actually happening. It's solving equations, and it's using equations in what are called transforms, Fourier transforms, that give you results in the imaginary world, or the imaginary, what we call a set of numbers. Okay? So again, it seems a little bit trivial at first as to why we're going to use this, but there are many applications. And the real thing you want to remember right now are these two definitions right here. Okay? So let's look at some examples of simplifications. For the first example we're going to look at here, let's say we have the following. Simplify the following. The square root of negative 36 and the square root of negative 32. So, by definition, and by what we looked at last time, what can I break up the square root of negative 36 into? What useful separation can I make here? Looking at the idea of what we did last time with the r and with the negative r into the radical. Chris?
Radical negative 1 times radical 36.
Yeah. Okay. And it seems like this is really trivial, and it's like, why am I doing this, right? But it's going to get more complicated, okay? So right away, square root of 36, Chris? 6. Square root of negative 1? Good. Now, traditionally, the way we write it, just so you know, when there's not a radical involved, is the real part, 6, and then the imaginary. Or not the real part, but the real number 6, and then the constant I afterward. Okay? So you're just going to write it in the standard form for now. So this tells me that, yeah, you know what? My solution is 6, which indicates that there was a 36 involved. The I indicates that it was really negative. Okay? Joe, part B.
Rated to negative 1 and 32. So you need 32 rated into 4 and 8.
Okay, but better than that.
12,
Keep going, you're on the right track.
just 8 and 4, and then break 8 into 2 and 4, and you get 4 I back to 2.
You're going to have 2 4s there, right? Which created a 16, really, right?
Oh, okay.
So that's the number you're forgetting there. Just make it easier.
4 I.
Good. So this becomes a 4 root 2 with an I out in front. Well, as Joe is saying now, if we have a radical involved, we can do 4i and then put the radical afterward. Okay? So your common form is going to be, if it's only a real coefficient like the number 4, just make it 4i. But whenever there's a radical, put it after the I. Again, just to reiterate, radicals will show up after the I if they're attached to it by multiplication. Any numerical or integer values that are in front that are rational will show up in front of the I. Okay, in front of the I. Easy enough so far? This should not be tough. Okay, we're just taking our negative 1. We're going to get to more complicated stuff, so I don't think it's time. Let's take a look at this one. Now we're subtracting and adding here. Okay? And we're still taking a look at our imaginary values. How do you know the problem is imaginary automatically? What's the indicator for you here? Chris? Yeah, there's a negative under the radical. Automatically indicates that there's got to be some imaginary portion. Julia, how about the first part?
You can split up. This is what 8, right?
Yep.
And
what should I put in the first one?
sorry?
What should I put in the first radicand?
Negative 1.
Good. And the second one, what looks like?
Negative 1.
Okay, so what does that become on each side?
I and 9. I believe that's in that. Down 8.
There you go.
And yeah, and then minus I. And then 25 and 4.
Okay, but square root of 100, make it easier. It's just,
10.
yeah. Because 25 and 4 works. Because you get 5 and 2, right? Which is just 10. Okay, so 8i minus 10i is?
Negative 2.
Good. Okay? Notice, this is something that a lot of students get confused about. You can get a negative answer still. Because they see that, well, you know what? We had negatives under the square roots, right? This negative 64 and this negative 100 up here. And we got rid of those negatives by making this I and making this I. So sometimes when students get a negative answer for I, they think it's not possible. Well, it's definitely possible here, actually. Okay? It just means that this is the imaginary component. Okay? The imaginary component is just negative still. It does not affect the problem at all. And don't let yourself think that because these were negative and we reduced them, you can't have a negative still. By combining like terms, we can see we still do have a negative. Okay? Kate, part B, please.
You're going to take out the negative 1 first.
Okay? And then break them up into what?
8 would go to 4 and 2. 19 goes to 9 and 2.
And notice Kate said it in that order. 4 and 2, 9 and 2. The perfect square being the one furthest to the left. Okay? Go ahead. Keep going, Kate.
And then I break this down to it's 2i radical 2 plus 3I radical 2.
Again, in that order. Continue, Kate, combine like terms.
And then it's 5I radical 2.
Good. It's not 5I radical 4, right, Kate? Okay, common mistake that a lot of people made on the last test. Root 2 and root 2 is not root 4. Okay, you cannot add those numbers together. This is like x and this is like x. 2I x plus 3I x. Well, that's just 5I x. Okay? So again, we're following the same rules as we did in the last section, as long as we remember those rules. Okay, and some of us need to study those rules a lot more. Hey Jared, how about you start us off with this one?
For a, could you factor out -1?
Good. So let's just automatically, you know what? Let's just take the shortcut now and just put an I there.
Okay.
Just for now on, okay?
So factor out I.
Good.
As square root of 9.
Which is?
3
Good.
times the square root of 16.
Which is?
4.
And I put the I there, right? Again, take a look. Notice each of these are negative quantities, so we need an I for each of them. Jared, what are we going to get when we multiply this?
12I squared.
What was I squared, Jared, by definition in the beginning? What did we say? -1. So the answer is? Yes, very good. Okay? Again, remember we said there were two definitions of I. First definition of I was I equals square root of -1. But I squared is by default then just going to be -1. So when we get something with I squared in it from this point on, we remember, let's replace it with -1. Okay, let's replace it with -1. Joe, part B?
Well, it's going to be 4I radical 2 times 2I radical 2. And that's it.
Now be careful. We have to multiply. It's not adding, so we can keep going.
Oh, yeah. Okay, so 8I radical 6.
8I.
Radical 6.
Okay, but you're missing something on the I.
Squared.
Thank you. And then squared means what? Okay, so again, back to here. I squared by definition is -1. So make this 8 times -1 times root 6. Or just -8 root 6. Okay? Notice what happens when you multiply an I by another I. It's no longer imaginary. It's kind of crazy to think about. You start with these two imaginary factors. Up here, for example, 3I and 4I. And somehow your result is perfectly real. Okay? And the reason for that is because, again, the definition of I squared is -1. So if you ever have an I times an I, it's going to get rid of the I. It's going to make it a -1. Okay? Does everybody see how Joe got this number here and this number here? The 4I and the 2I? Okay? He broke up the 32 and the 12 into 16 and 2 and 4 and 3. And then square rooted the perfect squares. Okay, good job, guys. Let's finish a little early. So, what I do want to show you, though, is this, okay, which we obviously talked about. But let's just make a quick statement about this. You don't have to write it. We can just read it together. All right. So the rule, root A times root B equals root AB, does not hold true if both A and B are negative. And this is what we have to talk about. Remember the last problem? Or let's take a look at this example right here. Was this?
Yeah.
This was part A, right?
Part A, yeah.
Okay. In part A, we had root -9 times root -16. If you were to multiply those two to start, wouldn't you get 144 under there? Because a negative times a negative is a positive. And then the square root of 144 is just 12. But what was the answer we got for part A in the last problem? -12. Okay, -12. And in this problem, we can't say, well, square root of 144 is plus or minus 12. We'll choose the negative root. The reason we can't do that is because we're not solving an equation. And only with an equation can we look at the positive or negative root. Jared?
If one of the radicals is negative, does the rule hold true?
The rule does hold true then, yes. And let's think about that. And let's show a quick example to make it easy on us. If we had negative root 9 times root 4, okay? If I multiply these two, I get negative root 36. Oops. Sorry, root negative 36, right? Which becomes just 6i. Agreed? If I simplify them, this becomes 3i times 2, which is still 6i. Okay? So if one of them is negative, we're good to go. It's if they're both negative that this rule is not true. Okay? Very good question. Example 4. Okay, so simplify these by the same technique as you would to rationalize a denominator. Okay, by the same technique you'd use as rationalizing a denominator. Remember, if we wanted to get rid of a radical 3 in the denominator, Joe, what would we multiply it by?
Radical positive 3?
Over?
Radical positive 3?
Yeah, okay. So now I want to get rid of an I in the denominator. What should I multiply the top and bottom by?
Radical I positive.
Close.
Radical positive 3I.
All right, you're on the right track. No radical needed. It's the same technique, but there's no radical here. Okay?
Oh, for A, yeah. Alright, so 5 over 5.
Okay. You could put the 5 up there. You could do this. You could say 5i over 5i. That's fine. But it's not necessary to put the I part. If you just put an I in both spots, watch what will happen now. What happens in the denominator? What does that become?
It becomes positive.
Slow down. The denominator, 5i times I is?
5I squared.
Okay. And what's I squared, Joe?
Negative 1.
Okay, so this is just simply negative 3/5 I. Okay? Believe it or not, this first problem here, which was 3 over 5i, we don't want to have I in our denominator, okay? We don't want to have an I in our denominator. The same reason or same technique as we use to get rid of a radical in the denominator. So instead of multiplying, like say we had this as, say that was our problem, we would multiply by root 3 over root 3. Okay, whatever this component here was, we multiply top and bottom by. The same thing now. We have this I here in the denominator. We're going to multiply top and bottom by I, which in the bottom will result in just a negative 5, because we have the I squared now. We take this part right here out in front as a coefficient and leave the I there. And it looks similar, but this I was in the denominator, and now this I is in the numerator here. Okay? Same exact approach. This one not as useful as rationalizing a denominator, but it's going to be useful when we look at the next section in 6.8, okay, where we have to think about complex numbers, which are imaginary and real numbers together. Okay? What about part B? Part B. 4 over negative root 3. Or root negative 3. I have to start pronouncing better, sorry. What do we do for this problem? Suggestions to get rid of that, radical on the bottom and the fact that there's definitely an I down there. Chris?
Would you multiply by root 3?
Okay, we can do that, but beforehand, let's take out the I first. And then we'll do that for sure. So what does it become if I take out the negative?
It would be I times root 3.
Good. And now, Chris, as you said, multiply by? Okay. And we also need to multiply by what else is in the denominator to get rid of? The I. Again, we don't want imaginary or irrational values in the denominator. Okay? I could put I root 3 and I root 3, or you just said root 3 first, Chris. That's why I put it in that order. Okay? But again, you could write it like this. Okay? If it makes this, because we've been writing in that order the entire time. Okay, what do we get when this happens?
Well, it's 4 out of 30 on top, and then does it come out to, which is negative 30 on the bottom?
Very good. It is negative 3. Because you have this. Let's take a look. We've got this I times I, which is I squared, or negative 1. So it's going to become really negative 1. And then root 3 times root 3 is just 3. So as Kate said, it's just going to be negative 3. Okay, so our final answer we're going to have, and this is going to get a little bit weird. Let's write it this way first. 4i root 3 over negative 3. Okay, that's how it looks to start. Now this is a kind of a weird one, and you can write it several ways. I would personally write it like the following. Like that. Whenever I have a fractional coefficient with an I part, I would write the fraction in front of the I. So I would write it as negative 4 root 3 over 3i. So I would take, again, this I quantity and move it over here as its own number. Take the negative, move it out in front over here. See the negative out in front. Okay? All right, last one. Last one. It might be 6, actually. Sorry, I think there's 6. So we're going to simplify here. So we're going to take a look at examples now if we have variables with negative coefficients under the radical. Okay? So negative coefficients, but we also have variables. So again, to do any of these problems, we have to remember to get rid of the negative part immediately. So make the imaginary part real. Okay, make the imaginary part real. Julia, how about this one?
Okay, so it's 3i, and then, well, you can actually 2i, so easier. Actually,
You could do it all at once, right?
yeah. So
I'm gonna leave it for 1 sec, but yes, Julia, you're absolutely right. Keep going.
yeah, and then plus I 9x, right?
Good. It becomes
And then on the left it becomes 2ix.
very good.
And then on the right it's 3ix.
Very good. Which together make?
5x.
Okay. No different than the last problems at all. So again, you take out the I component, you look at this and you say to yourself, well, let's see here. We've got 4x squared, which becomes 2x. That's easy, so it's 2ix. Here we've got 9x squared, which becomes 3x. We have 3ix. So we have 5ix. Okay? This is the only time you're going to see the I written before something else, really. Usually the I goes at the end and some number or some fraction comes in front of it. Here you have 5i and then x because the variable always gets tacked on to the end. Okay, another very applicable kind of question. Part B. Want to try this one? What do you do when you see a negative? Okay, so we're going to multiply them. Before we can multiply them, though, remember the negative came out as I. So we'll start by doing this. Okay, and then keep going. We multiply the insides. What's 6y times 3y? When I have y times y, it becomes y to the... Good. Okay, now, at this point in time, we have the 18. And we have to think about 18 as some perfect squares inside of it. What can you break 18 into that'll make it easier for us? What are the factors of 18? Go through all the factors. It's 1 times 18. 9 times? Good, 9 times 2. So let's break this into 9y squared times 2. Okay, and the reason, again, is take a look here. 18 is really 9 times 2, so we can do that. The y squared carries down. And now what we have is this part here, which is a perfect square. What's the square root of 9? 3. What's the square root of y squared? Yeah, it's just y. Very good. Those are inverse operations. So we have this I times the 3y times the square root of 2. And we can write this all in one line. Okay, so we'll write it as 3i, y, or let's say... It is kind of funky. What about this? Let's put the y at the end. And then 3 root 2 times iy. Okay? It doesn't really... I mean, at this point, you could write this several different ways. You could write it as 3 root 2 times yi. 3i root 2y. 3iy root 2. I mean, any of these ways are really fine. No, I don't think for this problem any way is better than the other. Okay? All right, last one. Last one. This is for real now. All right, so we have this equation in front of us. 3x squared plus 25 equals negative 35. Anybody want to tackle this one? Not super difficult, but something to think about. Joe?
3x equals negative 65, negative 60. X squared equals 20, negative 20. X equals root 4, 2 root 5. Oh, yeah, pull I out. So 2I root 5.
Okay, remember you're solving an equation. So there's two roots. Very good, Joe. So you notice that this became I root 20 with a plus or minus. And root 20 is really breaking up into 4 and 5. The 4 perfect square comes out as a 2. Okay, so this becomes a 2, leaving behind the root 5. So your solution set here is plus or minus 2I root 5.
I'm just confused. How does like a plus or minus I work?
How does a plus or minus I work? No different than a plus or minus some constant works. Yeah, so like for example, if your answer was not, say it was positive 20, it would be plus or minus 2 root 5. Now it's just 2I root 5. It just means that there's two roots, both of which are imaginary. Okay? And what you're going to notice is that imaginary roots are going to always come in pairs. And we're going to talk about that a little bit later when we're in chapter 7. Tomorrow we're going to do section 6, 8, and then we're going to move on to chapter 7 after that. And you're going to notice that imaginary roots always come in pairs, plus and minus. So if you have 2I root 5, you're automatically going to have negative 2I root 5. That's a trend that we're going to pick up on. Okay? Okay? There's my solution set written. Alright, so again, today's class was simply looking at what happens if we have a negative under the square root. Okay, what can we do with the negative under the square root? Your homework on this section is from section 6, 7. Notice, by the way, we skipped 6, 6. Okay, so we might come back to it later, but it's not as pertinent a topic as the other stuff, okay? So your homework from 6, 7 is going to be 1 through 23 odd, 26 through 36 even, and then 37 through 53 odd. It's going to be about 20, 22 problems total, okay? Or a little more actually, 25 problems. They don't take you a while, it's just a lot of problems. If you want to get started, I'm going to put a few up on the board right now. So it's 1 through 23 odd, so I'm going to put up the first few odds on the board so you can start. Let me stop recording.